Hi everyone. So we'll be picking up with today's lecture on chapter 11. So this is going to mark the end of what is traditionally general chemistry, and we're moving into organic chemistry now, which we'll be doing for the next several chapters. So this is going to be pretty much kind of a bird's eye view because it's usually like a 2 semester long course. So we're just going to kind of keep it to the basics of organic chemistry and the basics of reactivity. So just as a heads up, I'm not going to cover in this lecture sections 11.4, which is on the properties of alkanes. I'm going to leave that up to you to read because a lot of it is pretty straightforward and it's mostly just theory of like what are typical properties of alkanes. They're combustible or they have low melt TU. A good part of the chapter, and as it means molecule. So there's a good part on name. What we're going to do is we'll use, but I'm not going to recall compounds, but with it. All right, with that said, let's get started. So what is organic chemistry? What makes it different from general or bio or even inorganic chemistry? So the major distinction is because carbon is so important to life. Organic compounds pretty much are compounds made predominantly of carbon. They don't have to be all carbon. We're going to find out there's other things that can be attached like nitrogen, sulfurs, phosphorus, even halogens, right? But typically the name comes from, I think it's the 1800s or even earlier, extracting compounds from living things, mostly plant matter. So even things like aspirin, we actually derived that. That's been extracted from willow bark. So it's an organic compound. It came from a living organism. Though in general, we've expanded that term to mean any pretty much carbon-centered compound, or when I shouldn't say carbon-centered, but a compound predominantly made out of carbon. It doesn't have to come from a plant or even something living, but it's still going to have the name organic. So a couple of things that we need to pay attention to. Predominantly, this is going to be our definition, a compound made from carbon and hydrogen atoms. It's also going to contain, that doesn't have to be, but other organic compounds can contain nonmetals, particularly oxygen, sulfur, nitrogen, phosphorus, or halogen. And even though it comes with experience, all of those, including halogens, all those atoms, those elements, those are typically, those are what you need to live. That's what makes living organisms. And then they're also found in common products like gasoline. So if you think of what gas used to be, it's basically taking a living creature, like plankton or dinosaurs, waiting long enough with enough pressure and heat, and it turns them into gas. So they were alive at one point. Almost all medicines that we use, or even common things, I don't know why, yeah, shampoo, organic compounds, plastics, almost all, and then perfumes, but it's literally aromatic to mean smelling nice. That is a term in chemistry. Molecules that just tend to have a cyclic structure. So what's the major difference between organic and inorganic? Well, the major difference is that inorganic compounds tend to be made, they have high melting points. That's not really what's defining it, and high boiling points, but it's that they're usually ionic, or they're not centered around being made out of carbon, right? So an example that I have down on the bottom is an organic compound like this, propane, right? That's organic. It's a hydrocarbon. And then something like sodium chloride is an inorganic salt because it's made up of ions. So predominantly organic matter, though this is not all the time, usually is not ionic, though it can definitely be charged. And we'll talk more about that later. So all this table is really just a really big overview of comparing organic to inorganic. I'm not terribly worried about memorizing this slide, but the take-home message, what is organic? Mostly predominantly made out of carbon and hydrogen, and then sometimes out of these other elements. So you might have heard the term hydrocarbon before. If you literally break down the word, it makes sense for what an organic compound is. Hydro meaning hydrogen, carbon meaning carbon. It means they're predominantly made out of hydrogen and carbon. And so that's what we see down here. I got two examples, one of methane and one of ethane, right? We see it's made out of carbon and hydrogen. And then one term that we can add to our repertoire of definitions is a saturated hydrocarbon. It's as simple as meaning it only contains single bonds. So if we look at this molecule here, ethane, everything is a single bond. The term saturated literally means saturated with hydrogen. So it means if you did have a double or a triple bond, that you would actually, those would be considered unsaturated. It's saying that I could actually react it with more hydrogen to make it saturated. And we'll talk about that a little bit more later. But for now, knowing the terms is what I want. So we're going to start off by talking about alkanes. And then just as a heads up, and it's got to get used to pronouncing because it's a subtle difference in pronunciation, means different things. So we're going to have alkanes, and kind of a foreshadowing, we'll have alkenes, and then alkynes. So ENE and YNE and ANE, those are going to be the way that we verbally, and then also written later, distinguish between types of molecules. Shorthand is single bond, double bond, triple bond. And it has to be between carbons. So that's literally the basic definition of what an alkane, alkene, and alkyne are. So let's stick with alkanes first because they'll be the simplest. So alkanes are hydrocarbons, so they contain hydrogen and carbon, and alkanes only contain CC bonds or CH bonds. We'll add to that later, but we're going to start small. But we're going to find out later we can attach things to alkanes. They're usually formed by a continuous chain of carbon atoms, and so we'll talk about that later, but most organic compounds end up being a chain of carbon, and then depending on what you attach to those carbons determines its reactivity. A lot of what we're going to focus on to start with is going to be using the IUPAC system. That stands for the Internet, and it's no matter what compound, a unique. With alkanes, pay attention to certain cane, the name of, so euthane, that's why. On here, but yeah, after using Greek prefixes, they're going to have different names, counting in Greek. So what do I mean by that? So I'm going to have you guys memorize up until 8 on this. Well, actually, let's do all 10. It's not that hard, right? Because actually most of them are anything from 5 through 10. You already know that because these are the prefixes we used when naming compounds before. The only difference here is now we're talking about total number of carbons, and we'll see there's a pattern. So anytime we have a single carbon, it's usually called methane, and so that's why when we saw before when I drew CH4, we've used that example a lot. So 1 carbon, it's methane. 2 carbons, ethane. 3 carbons, propane, butane, pentane. And so you can see once we hit the 5, it starts going up in Greek. Pentane, hexane, heptane, octane, nonane, and decane. And so if we go here, you could go through and prove to yourself every single one of these. They're going to their name. So you guys will be responsible for knowing the first 10. Especially the first 4, because those are a little bit, they're A, more common to run across, and then B, they're new terms for us because we've counted in Greek before. So these molecules that we're going to draw are going to get bigger and bigger. Most molecules we've drawn have been pretty small. Organic compounds can get rather large. And so what we're going to need to do is probably switch the way that we draw our structures. So before, I've always really shown the expanded structure. So if I was drawing ethane, I would draw it like this on the board, where you can see all, sorry if it kind of gets, I got that line across the screen from the recorder, but we can explicitly draw all the carbons out. So other ways that we can start to draw molecules that are a little bit more simple. If I was going to draw, say, I might draw acetone drawn in. Oops, that's example. End of this carbon. And so do that explicitly gets a little bit right quick using the expanded color, like the couple for small molecules. But what happens if I'm doing something like decane or even bigger? This is going to be the way I draw molecules most often, because this is the most common way you will see organic compounds written. Is going to be the skeletal formula. So what do I mean by molecular versus skeletal formulas? So down here on the bottom, I have the example of butane. So that means I have 4 carbons, right? That's what I see, 1, 2, 3, 4. If I was going to draw that as a molecular formula, right, we can go C4, then I count up my H's, I get 3, 6, 7, 8, 9, 10, right? There's my molecular formula. I could draw it out, longhand, or I could draw it out the expanded formula. The quickest way to do it would be to draw butane like this, where it just it looks like a zigzag pattern. Formulas. Any single terminal point in the angle of those is going to be a carbon so that 4 bonds. Just go back, went and grabbed carbon from the C, we draw its dot messy. down the carbon. That's we're looking at the left-hand side. Must be to make it 4 bonds, to make it 4 bonds. Then each of these carbons in the middle, each carbon has 4. The brief view of using, and we're going to get a lot of practice with it. So if you're feeling shaky on it already, it's totally fine. So what I have here is just kind of a summary for one molecule of butane. So we have different ways to, draw the structure. This is how we used to draw it in lecture. Sometimes we might have seen the ball and stick model. This is when we use colored spheres with, cylinders to indicate bonds. The nice thing about this, it kind of gives you a sense of the shape of the molecule. So we can see that each carbon is tetrahedral. And so that means there's going to be 4 things attached to it. And so if we want to go back and look at, I think it was chapter 9, I want to say, maybe 10, I forget what it was. When we were looking at structure, right? When you have 4 things around that center carbon, each one is going to take on the shape of a tetrahedral. What I have down here in the condensed structural formulas, most of the structures, they're moving around these bonds right here. And so none of them are different. It just happens that move through space. We have here, and you can see why all that information. And so this, I was kind of foreshadowing earlier, not all compounds that we'll deal with, and these are actually very common, is we're used to drawing something like butane. There's my regular butane. But what happens if I connected those 2 carbons together? Well, what ends up happening is if I keep track of all 4 carbons, because originally I had 1, 2, 3, and 4, well, there's my 1, 2, 3, and 4. So that's called cyclizing the molecule. So what it means is I've closed it to make basically a closed loop. It doesn't have to be a circle, but as I add more and more carbon, it starts to look more and more like a circle. So we use the word cyclic. And just like we did with straight alkanes, what we can do is still use our skeletal structure to indicate what's going on with where the carbons are and where the hydrogens are. So now it's going to get a little bit more complicated. So naming alkanes was pretty easy when it was only carbons and hydrogens, because it was, all right, I either have methane, ethane, propane, cyclopropane, pentane. There was only certain ways we could name it. But now I'm going to have stuff to start hanging off by molecules, right? And what we call those things that hang off the molecule or decorate them, they're called substituents. So it means you've substituted a hydrogen for something else. What do I mean by substituting a hydrogen? Well, maybe I could pluck that hydrogen off and then stick something else there, right? Those hydrogens are mostly placeholders. So let's start off first with a simple substituent, where it is basically taking the molecule we started with, but kind of changing the way the bonds form. Not in form necessarily, but the way they're arranged in space. So these are going to be called structural isomers. So structural being shape, iso meaning same, and mer meaning pieces. So it's made out of the same pieces, but they're put together differently. So what I have here, we haven't seen it before, and I don't think we'll use this terminology, but I'm just going to use it to keep it straight, is something called N-butane. The N just means it's normal, which means it's a straight line. Don't worry too much about that. I could do the activity that I have there. My molecular form, CH4 hydrogen. Look at 1, 2, 3, 4, 6, 7, 8 hydrogen formula, page 10. The compound change how the bonds are. So you can go through this, the same number of hydrogens exist. Structural later that this is going to be 2-propane. That now, but just know you have a different compound. These are going to be called, because it's like a tree, it's forming a branch. So I've done this one out already, so it'll be pretty quick, but maybe pause the video and give yourself a couple minutes to try this out. It's saying draw 3 possible structural isomers of pentane. So what it's asking you have 5 carbons, and so I guess these are our rules, kind of, right? We have 5 carbons. Those have to be used up. We have 12 hydrogens. Those have to be used up, right? Each carbon can only have 4 bonds, and each hydrogen can only form 1 bond. Those are pretty much our rules for almost everything we're going to do in Orgo. Why? Because when I do the dot structure of carbon, I see that there's 4 spots on it to make a bond. Do the dot structure of hydrogen, there's only 1 dot. That's why. So, did a little bit of talking, but let's take a look at the structures. So these are the ones that I came up with. We can have basically the straight chain version, the straight chain pentane. We can rearrange it, so one of the hydrogens, maybe the one on, I don't know, this end, I just dumped it over here, replaced where I pulled it off with an H. So again, I can double check. I still have a C5H12. Or what I can do, maybe I take this H here and plug it on the center one too, and then I'll end up, again, with C5H12. Again, all carbons have 4 bonds. All H's have 1 bond. And I've used up all of my pieces, so I'm in good shape. So how do I start naming these things, right? So now I see how things can be attached, right? What we're going to look at right now is only 2 different types of substituents. And as we go through the chapters, we're going to add more and more, right? So we're going to start with just 2. The first is going to be alkyl groups, and the second one will be halosubstituents. So alkyl, anytime we see YL, usually what this means, not always, it just means it's an attachment. So when it's an alkyl group, it means an alkane has been attached to whatever your starting molecule was. Maybe it was an alkane, right? So you can have a big branch. And so basically group our carbon chains, and then top is we're going to use, so what we're going to CH3 attach, 1 carbon, methane, but now it's a squiggly line, but that'll become methyl, right? That. We can then maybe attach something, halogens, even in your body. Yeah, you do need fluorine. I'm pretty sure it's there. Things like that. Even vanadium, I know I mentioned that. Instead of calling it chlorine, we put fluoro and iodo. Here, this is a chloro on whatever my alkane. So these are the common groups, and we'll stick mostly with these because these are the most common. So when you have just 1 attachment, maybe it's just 1 CH3s coming off, that you start with a molecule, you attach a methyl group to it. That's what we're going to call it, methyl. Sometimes you attach 2 carbons in a row. We'll call that ethyl. You attach 3, propyl. You can go all the way down to decyl. I guess what is it? Yeah, it would be decyl, or dodecyl, which is 12. It's about as high as I know how to count. A new one, this is going to be different. It's called isopropyl. The reason for that is because, take a look, it's kind of, right, if I drew, I'm doing this, there's my, right, and then molecule, maybe I have to take an H attachment to a molecule, right, it's attached at the first position. But what if but instead of attach, I take a carbon, and now I attach through that propyl. So it means same, because it's a different carbon. We'll call it the 1 carbon attached to the 2 carbon. And then again, so let's do a practice problem together. So we'll kind of just jump in the deep end now that we have all this information. It's going to ask us to give us the IUPAC name for the following compound. Right now, you don't know how to do this, right? The subsequent slides we're going to go through are going to give us the steps on how to attack this systematically. But right off the bat, I see I have 2 substituents. So I have a chloro and a methyl. And sometimes it does get a little bit vague on what alkane, like the methyl, which one is actually a substituent and which isn't. What we're going to look at, you're going to try to draw the longest carbon chain you can, and that's going to be basically the center of your molecule. Like, that's the main thing. So what's highlighted in green. So we're going to say the chloro and the methyl are going to be our substituents, the one in yellow. So let's do this in a very systematic way. So the very first step is always to find the longest carbon chain. And that's what we've done already. So we see our carbon chain is 5 carbons long. 1, 2, 3, 4, 5. So my base name is going to be pentane. And now I'm going to start attaching additional names to this to build it up into such a name that it's actually going to describe the molecule I've drawn. So we'll start simple. We know we have pentane. Now what we need to do, this one's not always the easiest step, but it is required to make sure you get the correct name, is going to be numbering that carbon chain, because I have it labeled from left to right, but it's also possible to label right to left. Our goal is to find the carbon with the lowest number starting from the end nearest a substituent. So if we look here, this chlorine is only 2 away from the end of the molecule. So that's why I'm going to start basically numbering from this direction, Because if I started from the right-hand side, I'd be 1, 2, 3 away to the first substituent from the right-hand side. 2 is less than 3. That's why I've decided to inside of the molecule to the right. I do that with the name. Take a look at where we were in the quiz. After this, things just in numeric, because I've set up my number on the second carbon, third carbon, in between, or any letter here. And this is probably here people are saying, oh man, I have, yes. They're able to recognize what it just so happens. So like when you see here, methyl, if you get pentane and the rules just get overwhelming, but names can get quite long. Actually, the longest word in the English language is the IUPAC name for the protein titin, which is the biggest protein in the human body. I think someone read it out loud. It took 24 hours between a bunch of people just listing the name off to read the whole word. So it's kind of a little anecdotal side note. All right. So actually, we kind of did this. This is probably talked more about this already. So this we can go pretty quick through. But the idea of halo alkanes. So we did that in the last example. But right, there's my chloromethane. Don't worry about common names. I'm not going to use them. I'm going to try to stick with IUPAC. So we only pick one way to say it, and we say it that way. When once you get out into the quote-unquote real world, maybe people start, a lot of times you call compounds by common names. But to start off, I'm promising you we'll just do IUPAC. Right, and so we have our chloromethane. If I'm looking at the next one, well, there's my ethane, and I have a bromine attached to it, so it's bromoethane. 1, 2, 3, I got propane with a fluorine attached at the 1 position. So we have 1 fluoropentane. The reason why I don't have to have numbers for the first 2 is because if I attach the bromine at this second carbon or the first, they're both, the way I have carbon on the right is number 2. Around and put the bromine on, we'll take a look. Now it's 1. And anything bigger, though, I need to indicate the fluorine is on the, and actually very chemical, completely changes the chemical. Then in this case, I have to put 2 propane. It's the way, we have literally infinite amounts of molecules that you can put together, so we got to be really strict about naming, or else it gets very confusing. So what I've given you here is kind of like a backwards way. How do I take a name and then turn it into a structure, right? So the way you want to go through is basically in the reverse direction that we did before. So if I was going to draw this structure, right, I can break it down into several steps. I see heptane is my first, that's my base molecule. So I'll go 1, 2, 3, 4, 5, 6, 7. So there's my heptane. Then I can read, I have a methyl, 1, 2 carbons. I'll say 1, 5, 6. And so I have a methyl group too. And actually in the book, because with that, I'm just going to keep going with this. I don't like this. But so we have a methyl group on chloro group. Okay. I'm seeing the reason why, and it becomes, actually, I don't like this example. Example for you guys, let's do this. Sorry, it made sense when I put everything in real life. Make it heptane. How about that? New idea too, because let's go 1, 2, 3. It says I have 2 and 2. So 2 of them at the 2 position are too clear in our naming. We now have to start keeping track of Greek numbers, right? I meaning 2, so it means there's 2 methyls at the 1 position, right? So it's not start with, right? Name, you go from left, you go from right to left, back up. So let's do this. Let's draw the condensed structural formula for 3,1-chlorobutane. So again, we go through it step by step. Butane, right? So butane is going to be 4 carbons. So I'll try to keep the same color scheme I did in the last slide. So 1, 2, 3, 4. I see I have 1 chloro. So it doesn't matter what side. I'm just choosing that to be 1 right now. So now I'm going 1, 2, 3, 4. So I'm done with my 1-chlorobutane. And then it says I have a 3-bromo, and I'll do that in orange. So 1. We have 3-bromo, 1. The other thing that I know there's so many, it's almost sometimes good on the side. See, bromine comes before it comes alphabetically. So again, here are the steps we go through slowly through, and then we end up, with the same compound that I drew on the last screen. 1-chloro, 3-bromo, 3-bromo, 1-chlorobutane. And I know it's tricky. I have so many practice problems for this. I'm just going to give you a bunch with with the answer key. So hopefully, should be good practice. Theoretically, you can draw any molecule you want and name it. It's just not always easy. All right. So that is our kind of our whirlwind tour. I know it's a little bit quick. The hardest part is going to be naming for alkanes. So what we're going to do now is increase, not the not anything actually. The only thing we're increasing is the number of bonds in the molecule. So alkanes are traditionally pretty unreactive, other than being good for combustion. Alkenes and alkynes are going to be a lot more reactive than alkanes, and we're going to find out. And it's usually because it's either high or low electron density usually gives rise to chemical reactivity. So when you had something like, ethane, right? There's pretty much electron densities spread evenly out through that entire molecule because everything's nonpolar. But when we have something like this, ethine, right, or acetylene is the common name, having electron density molecule is going to make it very reactive in acetylene. So right here is basically just a summary. We're applying the same rules that we had for alkanes. The only difference here is alkenes and alkynes. All alkenes have a double bonds. All alkynes will have triple bonds. And so we can see how the names change. So ethane, ethene, ethyne. And what we have down here, I kind of went up in complexity so you can see the structure. But propane, propene, propyne. Propyne does look a little bit weird, but if we put in our carbons, it's a C connected to a C, triple bonded to a C, right? So it looks a little weird because it's in a straight line, but there's something to get used to. So what do we do with naming if we have alkenes and alkynes, right? So what I have is basically doing two at once, right? So we're going to follow really similar rules, except the double bonds and triple bonds are going to take precedent in terms of what's the main carbon chain, and then also it's going to dominate which side you're going to count up from, and I'll show you what I mean in a second. So having the double bond here, I'm looking at A. So 1, 2, 3, and it actually doesn't matter if I go 4 here or 4 there. It's symmetrical. Right, so we can keep it like that. When I'm determining how to, right, if I did it this way, the difference for 2-pentene. Same thing. Again, we went 3, 4, 5 we're counting in the right direction. 3, 4, counted wrong initially, and then and it's at the 2 position. So again, this is kind of going slowly through it. So we have our pentene and our hexyne. Figure out where the methyl groups go. At least in part A, I have a substituent for the methyl group, and so it becomes 4-methyl-2-pentene, pentene. Again, more rules. I know the 2 here, it's, what I was talking about, things coming alphabetical. The 2 is connected to the ene, so that 2 can't go anywhere. But if there were more substituents beyond this methyl, you'd have to order them alphabetically. So other properties. So now that we've introduced double bonds into a molecule, when you have single bonds around a carbon, you can actually think of that almost like a pinwheel. So if there's a bunch of hydrogens attached to it, it can spin around that bond, around that, like it literally is a cylinder. It can spin around. However, when you have a double bond, though, you are no longer allowed to spin. It's stuck that way. And so that is going to determine if things are pointing up or things are pointing down. Do this. I'll put a chlorine on this. One chlorine pointing up drawn. Those are chemically distinct to determine if same side or on opposite side. Be using the cis isomer. Cis, same side, means they're going to Latin words for cis and trans fat double bonds where a little bit on that. You hear about good fat. They don't use the term, but good fat, quote unquote, is cis fat, which means when you draw out the structure, you're going to have a cis isomer instead of a trans isomer. So what I have here on the side are 2 molecules. They're both isomers, so they're both have the same chemical compound. So if I go through 1, 2, 3, 4, oops, wrong tool. C4H10. We already talked about isomers before. Not H10. It's going to be H9. Or H8. Hold on. 3, 6, 7, 8. H8. right? The only reason I could correct that so quick in my head is I realized there's a double bond there, and so there has to be less hydrogens than butane, because you have to pull hydrogens off to basically make room for the double bonds. So both are C4H8, but we can see here both of the methyl substituents are on the same side of the molecule. So it's going to be cis-2-butene, because we have our 1, 2, the double bonds across the 2. And if we look here, we're going to have a trans-2-butene. Group is pointed up into the double bond, and the two groups are each other. So when we're naming things, this is where the cis comes at the very beginning of the compound name. So again, we want to make sure we're labeling things right. We only have 2 carbons here, 1 and 2, because it's attached to bromine. So we can see we have a bromine on the 1 and a bromine on a 2. So there's my 1, 2. I have 2 bromines, so it's di, bromo, and then my 2 carbons, so ethene, and the ene because of the double bond. And then to indicate that both bromine are on the same sides, there's my cis name. Can do the same thing for this other trans isomer. So I only have 2 carbons, 1 and 2. I have a bromine on carbon 1 and a bromine on carbon 2. So 1, and so dibromo. And then the bromine are on. Again, it's going to come down with practice. I can say them, but until we do it, I feel like this is more just to get the theory across. So we're almost done. I think we have 1 or 2 more sections, so we should be able to get through this in the next 10 minutes, hopefully. So what I'm looking for is to only know 2 types of reactions to start off with, and it's pretty much only going to be reacting with alkenes and alkynes. And what they're going to form, one we already know about, is going to be alkanes, but we're also going to introduce the idea of an alcohol. We'll spend more time on alcohols, but effectively what alcohol is, I'll use squiggly lines to mean it's a molecule. Somewhere attached to that molecule is an OH group. So that's why when we've used examples in the past, like, I can draw the stick structure now, right? In the past, when we've done with ethanol, well, there's my eth, 1, 2, oh, this is propanol. We'll just do it, yeah, whatever. 1, 2, 3, propanol, right? So if you're using things to disinfect right now, probably using propanol or isopropanol. Isopropanol looks like this because I'm iso. Same molecular structure, just putting that alcohol group in a different spot. Don't worry about too much about that. It kind of went off topic. We'll do a whole, there's like a little bit of foreshadowing. Reactivity. Reactions. Hydrogenase, familiar, like partially, actually this is the, and hydration. If you look at the names, it kind of hydro, meaning water. And right now we'll focus in a little bit. Any kind of alkenes, there's a catalyst, like it's going to give an alkene and strong acid. And so if anyone let converters in pollution, and the reason why converters are so expensive is converters. So when gas don't completely alkynes, which are more alkenes, so as the converter, so what do these reactions look like? Right, so we'll start with hydrogenation. All it is taking an unsaturated or hydrocarbon. So unsaturated means there's at least a double bond. So in this sense, we have an alkene. That means if it's unsaturated, it means there's more space that I can put a hydrogen on. So what we can think of this as is breaking one of the double bonds, which will create, if you take the bond apart, there's 2 electrons in there, right? So you could theoretically think of those 2 electrons now ready to accept a bond. If I broke apart that H2 molecule back into its dot structure, what we see is both of those H's would have 1 electron. So now, it's kind of weird the way I'm drawing it, but those electrons, you broke my double bond, those extra electrons can form new bonds, and then it literally is adding the hydrogen phrase, is adding, so it lists 2 H's and then just carbons across the double. Example for an alkyne, palladium again, but unsaturated. That means I have twice, because, and then I can break the other double bond equivalent with the molecule. So take home hydrogen across double and triple bonds. Hydration reactions are going to work very similarly. The only difference is instead of having a platinum, palladium, or nickel catalyst, you're going to have a strong acid such as H2SO4. So in this case, there is a directionality to it, but it's a similar idea. It's adding water across the double bond. So one of the H from hydrogen, from the water, one will go there, and then the OH will go to another side, or sometimes it flips. And actually, you'll get a mixture of both reactions when you conduct a real reaction. So again, it's just taking a molecule that has a double or triple bond, and then you're adding water across it. So an H will go to one side of the double bond, and an OH will go to the other. Just always double check to make sure that there are 4 bonds to every carbon. Let me write that down. So we'll start adding to our list. It's always 4 bonds for carbon. For hydrogen, a new one, oxygen. This is how you can double, because we see for the oxygen, it's implied. So this is the last thing we'll talk about. We're not going to deal with naming. It's mostly just recognizing what aromatic compounds are. So what we've done is we've taken a couple ideas here. We know we have alkanes. If I add more double bonds to them, I can turn it to alkene or an alkyne. We've already seen that we can make cyclic molecules. What happens when we join this idea together? And this is when we get aromatic compounds. So you might be able to see here, but what an aromatic compound is, it's a cyclic compound. So what I have over there, I'm not going to draw the hydrogens in, and it has alternating double bonds. And so it's actually those double bonds, we're not going to get into this, they actually can resonate, they can actually flip around, and in real life, because it's based on quantum mechanics, you get this weird spreading of basically 1.5 bonds around everything. So it's constantly moving. But that's what we're not really worried about too much. We're just worried about a cyclic molecule with at least 1 double bond, right? And aromatic compounds are more than that. Instead of being cyclic alkenes and cyclic alkynes, it's when you have this benzene structure. So what do I mean by benzene? Oops, that's a little bit too dark. Right, when we look at benzene here, we'll deal. What we see is we have those alternating double bonds inside that cyclic structure. And what this is called resonance, and we're not going to get into it, but the take-home message is, if you look here, like I drew in that last slide, those bonds can basically, they can move around as long as the 4 bonds to carbon are always held. As long as that rule isn't broken. The way we usually draw that is to say, well, it's not really moving, but it is acting like a cyclic bond. Like it is literally behaving like 1.5 bonds throughout the entire molecule. And the way we draw that as a skeletal structure is to have basically this ring and the double bonds, and then they form this cyclic. So don't get too deep in benzene looks like, looking forward. And then to know from there, they tend to smell, they usually smell good, not always. But just to give you some context, benzene is actually a very common structure in organic chemistry. And so it has wide variety of uses, both in industry, in your body, in nature. So a couple of examples that I showed you is like TNT is 2,4,6-trinitrotoluene. So where does the name come from? Trinitrotoluene, TNT. Toluene is just a particular derivative of benzene. So you have your benzene ring. Toluene just means there's a methyl group coming off. Don't worry about that too much. It's more just background. So we can see there's my benzene with the methyl group coming off. There's my toluene. And then we won't get to this and maybe till later, but then we have 3 nitro groups hanging off. But don't worry about those. We haven't talked about them yet. But we can see that's where TNT structure is coming from. Or something that's a little bit more innocuous, like phenylalanine. So phenylalanine is a amino acid used to build proteins. We'll get into that a lot more when we get to, I think it's chapter 6, protein chemistry. And then it's also used in a lot of other compounds, right? Stuff that you've eaten. So vanillin. So, oops, that's the last slide. So vanillin is, when you have vanilla extract, that's what you're eating, right? It's vanillin suspended in ethanol. Ibuprofen, when you have a headache, well, there's your benzene ring in the middle. Acetaminophen and aspirin. We'll talk about later when we get into enzymes why you start to notice, all 3 of these here, other than vanillin, right? Acetaminophen, aspirin, and ibuprofen all are pain relievers. There's a reason for that. Similar structures will bind to similar proteins in your body. So that's why, even though they're mostly different, but there's similarities, It's because they're interacting with the same proteins, and proteins recognize structure. So, all right. I know there's a major take-home going to be naming, as well as knowing those two nation and hydration. Learning individual reactions, which means you can apply one type of molecule. Alkyne, and I say list with hydrogen. I'll see you all tomorrow to chapter. So what I would do is read the questions based on other because they do. Even if you're not 100%, a lot of these 14 as well. And still staying healthy.